Here it is. So, and then in problem 3, we actually gave you a regression line. Now, the regression line that we gave you, it turns out, this is it right here. In the homework, it was actually a blue line. And we also gave you the formula. So remember, if you remember algebra, again, a flat line is y equals something. And a sloped line follows the format of y equals mx plus b. So x being, x, m being some, coefficient on x, and then b being a constant value that adjusts the height of the line. So we actually gave you this formula, and that was, we said weight, or y, is equal to 1.6x plus 43.5. Right? So we gave you that. And if you were to plug this into a graphing calculator, you would get a line that looks just like this, same slope. Let me recenter that. Okay. Now, so in this case, we're still going to do, and I'm going to write this formula again up here. So we're still going to use this this formula, but instead of plugging in the same average every time for the predicted value of x, we're going to plug in the value that we get out of this equation. So we're actually going to use the formula of this line to predict each value, and as it turns out, our data falls on a line roughly, so we should get a much more accurate prediction with much smaller error numbers when we do this, right? So our first one, we're going to say, and I don't actually have, I should probably have printed this, but so our first individual, who is our shortest individual, let's start down here. Shortest and lightest is this person, who is 57 inches tall and 134 pounds, right? So if we plug that in, we don't actually know their weight. We know their actual weight, but our prediction is going to use this line to guess their weight, and it turns out it's going to get almost exactly the right answer. But so what we would do is we would say y, for this person, y is equal to 1.6 times their height, which is 57. 1.6 times 57 plus 43.5. So that's pretty easy to do the math for. I'm going to do it right now. 1.6 times 57 is equal to 91.2 plus 43.5. And that's 134.7, right? So it looks like in the answer guide that you guys can see, this was actually rounded down to 134. Whatever, it doesn't matter that much. But as you can see, like, it was really darn close to the actual height, only 0.7 off. So if we were to actually draw the error bar here, which is too small to see, it would be 0.7, right? So our first individual's error is 0.7, right? And then we'll do the next one too. So this next person is 136 pounds and 59. So again, for the second person, y is equal to 1.6 times 59 plus 43.5. I can't write very well, can I? Point. So again, 1.6 times 59 is 94.4 plus 43.5 equals 137.9, right? So 137.9 is the predicted value, for this one. So again, we're plugging 137.9. Let me write that down. We would be putting 137.9 here for predicted, and then the actual weight of this person was 136 pounds, if I'm not mistaken. Yes, so 136 minus 137.5, or 0.9, is 1.9, negative 1.9. So you can see right here and right here, we've got our first two values. So we're going to continue on like that. You know, 0.7 squared ends up being 0.49. And negative 1.9 squared is 3.61. So again, what we're doing is we're measuring these distances. Same data, by the way. This is the exact same data as the last graph, but see how much shorter and how much less I had to draw for the errors? Even when we square these, which makes the numbers bigger, we're still going to have much lower number. So I think what I really wanted to show you guys visually here was, do I have the other ones now? Yeah. Compare when we're doing regression with a line, our error bars are so short, whereas when we're doing it with this, you've got way longer errors, and so they all get squared. We get a much higher number. We get 64.5 here. If I continued on this one and did all the math for the other four individuals, what we would actually get, final answer, is 4.6. And what a lot of you guys did that threw you off was you did all this just fine, and you got the number, you know, the sum of all these, but then you averaged them all. You know, you squared them all, you did this part of the equation, and then you took the average of that and then used the average. And when you did that, all you did was draw a flat line like we had when we did problem 1. And if you do that, now your errors are, you know, if you draw a flat line here, all of a sudden your errors are much bigger again. So that defeats the purpose. What you need to remember to do is not to take the average, but when you're going through each iteration of this you know, equation, to actually solve the you know, y equals mx plus b and plug that number into the predicted value, not the average of all those. And that way you get a really nice, accurate prediction that's really good at predicting, you know, it's really good at finding and predicting patterns in any kind of, you know, multivariate data that has a linear correlation. It goes up, you know, like as one increases, the other one increases along with it. Not so good at doing things like exponential growth, but you know, if you're worried about that, you can take ISTA 116 and learn more than you ever wanted to know about predicting and finding patterns in scatter plots like this. So I think that went a little longer than I wanted it to, but hopefully you guys will still find it useful and have fun studying for whatever.